Okay, so here we are, one-dimensional kinematics, and we just have it defined here. What is kinematics? Kinematics is the science of describing the motion of an object. So most of us know just from our everyday lives that forces cause things to move, okay? But in this first section of Physics 20, we don't actually have to worry about the forces, and we can still sort of describe the nature of an object's motion without knowing about the force. That comes in the second unit. That unit's called dynamics. Right now we are working in what's called kinematics. Okay? So the first thing that you would ever really learn in a physics class is the difference between scalar and vector. Okay? So scalar, underline it. Scalars are quantities fully described by magnitude. And magnitude is just a numerical value. Think of it as like the size. And a scalar is fully described by magnitude only. Okay? So it's just a number. Whereas a vector, and these two guys go hand in hand. You cannot mention a scalar without mentioning the vector. Now the vector, these are quantities fully described by magnitude and direction. So by both a magnitude and a direction. Okay, so in kinematics, with the study of motion, a natural place to start will be distance and its vector counterpart. What's the vector counterpart for distance? Displacement, good. And speed, what's the vector complement of speed? Velocity, good. Okay, so if I say speed or if I say velocity, in your head you're kind of like, isn't that the same thing? But in physics, no, they're not the same thing. And same with distance and displacement. Is it the same thing? No, it's not the same thing. One describes only the number, while the other has both the number and the direction. Okay, so a vector needs two things. Okay, you can think of it as like almost an XY component. You have a magnitude, comma, you have a direction. Okay, two components. Okay, so let's start off with the more natural place, distance. So how am I going to do this? Add a page. Why doesn't it just keep my line? Stupid program. I do this every time. Okay, so distance, underline it. Distance. Okay, so distance is thought of as how much ground an object has covered. Distances are scalar. The symbol for distance is d. After distance, we'll talk about displacement. Underline. Displacement is a vector. Similar but different. While distance is how much ground an object has covered, Displacement is how far out of place an object is. How far away is the object from where it started? That is displacement. Okay, so let's write that down. How far out of place? And of course, it is, in other words, the overall change in position. So often you have this commonality in the language. If people use the word displacement, they can also use the word position. Okay, so those are interchangeable. So we have these things called position time graphs, and it's just a displacement time graph. Okay, and the symbol for displacement is also D, but we put a little arrow on top of it like this. That little arrow denotes vector. Okay, and I'll just write it on the whiteboard so you can see it clear. Like that. Okay, let's do an example. Okay, physics man travels 4 meters in this direction. What direction is that? Yeah, we can use right and left. We can also use east and west. So we've traveled 4 meters right, or we've traveled 4 meters east, however you want to look at it. Then physics man travels 2 meters down or south, however you want to look at it. And then he travels 4 meters west, and I apologize for those not being straight lines. And then he travels 2 meters north. Very, very common example for just understanding the difference between distance and displacement. Okay. So how much ground has physics man covered? So the distance is 12 meters. But how far out of place is physics man from where he started? So the displacement is 0 meters. And if your displacement is 0, you don't really have a direction. So like when it's 0, that's like the one time you don't put a direction, right? So your vectors should have a comma and then a direction, but if it's 0, there is no direction. So okay, any questions on this? All right. So the 12 meters is the ground covered, while the displacement is direction aware. So we can put a little note on that. Displacement is direction aware. It is aware of direction. Okay, so the 2 meters south cancels the 2 meter north, and the 4 meter west cancels the 4 meter east. Pretty straightforward, yeah? That's a Science 10 concept. Let's move into speed. Okay. New page. Of course, it doesn't have lines. Choose background. Why did they make me do this? Okay. Speed. Speed, this is the one that you could connect to your everyday experience. what would you think of as speed? You would think is, how fast an object is moving. Everyone is sort of aware of this one from just life. How fast an object is moving. Okay, it is a scalar. Now, in other words, i.e., do you guys hear that? Probably like subwoofer.
Sorry for the interruption. Jared Black, report to the office, please. Jared Black, please come to the office immediately.
Okay, so let's finish off this definition. Because how fast an object is moving is more or less like how you would describe it to a layman. A proper physics definition would involve the word rate. You guys know what a rate is? You'll probably learn this in junior high. A rate is just a ratio with different what? Different units. Okay? So it is just the rate at which an object covers distance. And of course we would use the distance and the time. So the numerator would be meters, typically, and the denominator would be seconds, typically. Okay, so that is speed. So you can say that I drove to school on average, 60 kilometers per hour today. That's a speed, okay? Now, let's jump into velocity. Oh, the symbol for speed is just v. Now into velocity. Velocity being a vector, it is direction aware. So velocity is the rate at which an object, and we can contrast this with speed. It's not the rate at which an object covers distance, but it's the rate at which an object changes what? Not distance, not ground covered, but yeah. And what's a better word for direction? We used it with displacement. Starts with, yeah, position. Okay, so the rate at which an object changes its position. And the symbol is going to be V with the little arrow on top. So V with the arrow on top. Now watch me, I'm going to do a little dance. Is that wild? Was there a lot of speed in there? Yeah, a lot of speed, right? But is there a lot of velocity? No, because I keep returning to my original position. So there's a lot of speed, but not a lot of velocity, right? If I make it weird, you'll probably remember it. Does that make sense? Your speed is related to your distance, so that's the ground covered. But the velocity is related to the displacement, so how much position has changed, okay? So if I drive all the way home and then drive back to East Glen, what was my average velocity? 0. Even though I did drive a speed, right? Correct, unless I parked somewhere else. Good. Okay. And just for clarification, I know this is obvious, but velocity is in the same direction. Because velocity is direction aware, it's in the same direction the object is moving. It seems obvious, but we'll just write it just to be clear. It's always in the same direction the object is moving. So if the object is moving eastward, its velocity is eastward. All right. So, like when I drive to school today, do I always go the same speed? I'm constantly speeding up, speeding down, braking, speeding up, stopping, speeding up. So my velocity is always changing, right? Do you agree? Right. So there's this thing called average velocity. And there's this thing called instantaneous. Instantaneous. So the instantaneous velocity is in the moment, in the instant. That's where they get the word from. So whoa. So this is in the moment. Like in the instant.
Excuse the interruption. Omid Rajab, please come to the office. Omid Rajab, to the office, please.
And the average velocity can be thought of as, well, an average. An average of all my, not my, but an average of all the instantaneous. Instantaneous. So if I was to average up all my moments, I would get my average velocity. So say I was going 60, then 62, then 65, then 67, then 49. And would that take a lot of work to do that? Yeah, it is. So there's your speed in the moment, and then there's, or your velocity in the moment, and then there's your overall speed, okay? So if it took me 30 minutes to drive, I don't know, 20 kilometers, how fast on average was I going? You know this. It's very simple. You just use your standard VDT formulas, which you know from Science 10, okay? So let's write those down. Okay, so this equation here, you should be aware of it. D stands for? Good. T stands for? Good. And this V average stands for? Which one goes with distance? Speed. Okay, now if I write it like this, and you okay with the AVG, that's average, right? If I write it like this, we're no longer working with speed, but we're working with velocity. Because now, instead of working with distance, we are now working with displacement. Okay, and of course, it's still time. Time is scalar. Okay? So, I'll give you another form of this displacement over time. Is just the change in position over time. Okay, so just for clarification, this symbol here means change. And it's often found just by taking the final position, subtract the initial position. That's this delta. Delta. Okay, let's do an example. Okay, so we have a runner covering distance. At a constant speed. So you could just imagine this. The runner gets going, it's accelerating at first. And then if you started to track the runner, let's say it's like a long distance runner, they're probably reaching some constant speed that they can maintain where they're, if you track them over certain minutes, maybe every minute they covered a certain amount of distance. And they kept this pace up, and they kept it the same. That would be called a constant speed, okay? Now in the moments, like when you're first getting going, yes, you're going to be accelerating and your speed is changing, but eventually you'll reach some constant speed, okay? And let's just make up some numbers and build a chart. So we have this chart, time in seconds versus position, not position, we'll go with distance in meters. So we'll just assume that it's constant all the time. So we're making this a little bit simpler than what actually would happen, but just to keep things simple, to make our point, make up some numbers. So this is an example of constant speed. How can you tell that it's constant speed? As we go up by 1 in the x, we're going up by 6 in the y. Straight line, they call this linear if you were to graph it. If you were to look in a physics textbook, they would call this uniform motion, aka constant. So it might look something like this, where you have your time and your distance plotted, y versus x, and you would be going over 1 and up 6 constantly. The next one, over 1, up 6, over 1, up 6. Okay? Change in distance is 6 meters. Change in time is 1 second. Delta y over delta x equals 6 meters for every 1 second. How fast is this person traveling? 6 meters per second. This is our slope. So we come to realize that the slope of a dt graph is speed. Okay? Okay. New page. All right, here we go with acceleration. Again, this is something from everyday life that most people are comfortable with, acceleration. And acceleration in everyday life is like if you accelerate in a car, maybe you're going from rest where you're not moving and you're getting faster and faster and faster. Okay, so what is changing with acceleration? Your speed. So if you're speeding up, you're accelerating. If you're speeding down, you are decelerating. Good. Okay. So acceleration is a vector. Okay. And it is defined as the rate at which an object changes its velocity. So if your velocity is changing, are you accelerating? Yes. If your velocity is constant, are you accelerating? No. Okay, we can represent this in a chart. Time in seconds versus velocity in meters per second. So let's say at 0 seconds you're traveling 0 meters per second north. And after 1 second you're now going 10 meters per second north. And after 2 seconds you're going 20 meters per second north. And so on. Okay, so is the velocity changing as time goes on? Yes. Therefore, we are accelerating. Are we accelerating at a constant amount? Yes. What are we constantly going up by in our velocity? Going up 10. Okay? This is an example of constant acceleration. Now, in everyday life, usually things don't always accelerate at a constant rate, but in physics 20 and 30, you will always only have constant acceleration. In order to solve problems involving non-constant acceleration, you need calculus under your belts, and we don't have that. So everything we will be doing will have constant acceleration. Okay, so what this would look like on a graph. If you were to graph velocity versus time, you might get something like this. So as we go delta x of 1, we have a delta y of 10. Every time we go over 1, we go up 10. Over 1, up 10. Over 1, up 10. Okay? And we have delta y over delta x. Okay? What unit is my y-axis? Meters per second. Good. And what unit is my x-axis? Second. So we get this new derived unit of meter per second per second. Meter per second per second, which is just meter per second squared. Okay, so that's the unit for acceleration. It's every second your meters per second changes. So it's meter per second, meters per second squared. Okay? So this is slope. And we come to realize that the slope of a VT graph is your acceleration. Now, slope is constant, so what this yields for an AT graph, oops, if we were to graph A versus T, and this is for physics 20 and 30 in Alberta, we only will ever graph constant acceleration. Okay? Your acceleration will never ever look anything different than that. Okay? So constant acceleration. Questions so far? Okay, one last section on graphs. All right. Okay, call this one graphs. Okay, we need to imagine an object on a line moving. So just mark off some equidistant points. And we can say that this is time at 0 seconds, time at 1 second, time at 2 seconds, time at 3 seconds, time at 4 seconds. So as time goes on, we can say that the position of some object, which we can draw in as a purple dot. Okay, that's the object, my purple dot. And let's just say that displacement can be measured. Say at 0 seconds it's going 0 meters. At 1 second it's at 10. At 2 seconds it's at 20. At 3 seconds it's at 30. And at 4 seconds it's at 40. Okay, for a rightward moving object. Rightward moving purple object. All right, so by looking at this object, you have to imagine that at each interval of time, it's changed its position. Would you call this uniform or non-uniform motion? Good, this is uniform. Why is it uniform motion? Not acceleration, constant velocity, which means it has no acceleration. Yeah. So would your graph be linear or non-linear? Good, you'd have a linear graph. Good. Now let's imagine the purple object accelerating. So we draw in a line. Now this time you're going to mark off some points that start off close but start to get farther and farther apart. And I can use my purple dot object. Now let's think about this. And again, we can do something similar with time. We can say time here is at 0, 1, 2, 3, and 4 seconds. And we can say displacement is 0, let's say 2, 4, 8, 18, 32, and this is meters. So meters per second. What's the speed at the second dot here that I'm pointing to? At this dot, what's the speed? 2 meters per second. At right here, what's the speed? 8 meters covered in 2 seconds would be 4 meters per second. And then here it would be 6 meters per second. And at here it would be 8 meters per second. So what's happening to the speeds or the velocities? They're increasing. So we can say that this graph is, or pardon me, this object is accelerating. Good. So if the object's accelerating, the speed is changing. We call this non-uniform motion. Because not constant velocity, it's non-constant velocity. So would the graph be linear? Of a position time graph would not be linear, it would be curved. Okay, so you can either have a straight graph or you can have a curved graph. That's all you can have. It's either straight or curved. Okay? That's curved. And then stuff that, like pointy graphs, that stuff doesn't really happen. There's never these like sharp turns like that. Unless you start talking about like some purely mathematical like ideas. But in real life, it's always either smooth or straight. Okay, and this is also for a rightward moving object. Okay. Non-constant velocity, the velocity is changing. This would, the first thing we have would be a linear graph, and the second thing we'd have would be a non-linear graph, or just a curved graph. So basically linear versus non-linear, constant versus non-constant, uniform versus non-uniform. All sort of the same words for the same thing. Okay, so this is just going to be your last slide of notes coming up. So if you're getting sort of impatient, we're almost done. Okay, so now we got, let's draw some DT graphs. Okay, so some DT graphs. So position time graphs. I wish I had like a copy paste. Maybe I do. Nope. Maybe there's a group. Can I group? Can I select two at the same time? Nope. Well, maybe I could drag like this. Oh, sweet. Copy. Paste. Oh, yeah. Okay. Let's draw in some graphs. Let's compare. Let's look at those two graphs. Which one's moving faster? Good. Because slope has to do with speed for a DT graph, if it has a steeper slope, it has a higher numerical value, has a higher magnitude, and therefore a higher speed. Okay? Also, in both cases, the slope is positive. So that tells us that we are moving rightward if we're traveling horizontally, or northward if we're traveling vertically. Okay, so let's just assume we're going horizontally. It's one-dimensional kinematics. So this is slow rightward because of positive slope. And we can see here constant velocity. The graph over here is going to be fast and rightward. The rightward has to do with the positive slope, and the fast has to do with the steepness. Constant velocity. Carry on, you guys. So too bad you guys don't have a paste tool, but you're going to have to sketch these in quickly. Notes are fun when you only have a pen and a pencil. Okay, so let's take a look at these graphs. Similar, but different. Which one is going faster? What does speed have to do with these graphs? The slope. Which one has a steeper slope? The second one. So the second one is still is faster. Okay, the second one is moving faster. But which direction are they is the object traveling? Is it still going to the right? No, it's traveling to the opposite, which is left. If we're going north, now we're going south. Okay? So again, it's slower, but now we're going leftward. And that has to do with the negative slope. And on this graph here, it's also moving faster, but we're going leftward because of the negative slope. And again, they're both constant velocity because of the linear shape. Okay? So just to reiterate this fact, because you might forget it, this positive and this negative has to do with slope. Same with this. It's slope. Graphs that rise to the right have a positive slope. Graphs that fall to the right have a negative slope. Okay? So imagine you start at the origin. I'll use my pointer. Imagine you start here at the origin. You're at your home base. You're at home. You ride your bike at a constant velocity to 7-Eleven. You grab a Slurpee. Okay? And then you travel back here. What's happened? Boom, boom. Are you back home? Yeah. Imagine your home to 7-Eleven was a straight line. To get to 7-Eleven, you have to travel rightward. How to get home? You'd have to travel leftward, and you'd be back home. Does that make sense? If you lived in a one-dimensional world. Okay, we need another page. Oh, the paste tool. Save my life. Alright, let's check out this graph. A little bit different, eh, of a graph? What makes this one different? It's not straight. Oh, this one's tough to draw. Alright, there's two graphs. Which one of those objects is moving faster? Can you tell? I don't know if we can look at them together. Why don't we look at one individually? Good. Does this one start off slow and become fast, or does it start off fast and become slow? Okay, so imagine we could draw little lines on it, because we know how to look at slope, right? Let's imagine we are drawing some slope lines, and these are called tangents. And if you're in calculus, are you in calculus? You next semester? So if we drew a slope of a tangent line, you guys know what a tangent line is? Crosses at one point. If we to just pick points on this curve and draw tangents, what's happening to these tangents? They're getting steeper. Would you agree? So if it's getting steeper, it starts off slow and gets faster. Okay? So that's this one. Slow to fast. And in which direction? Right or left? Why? Good, negative slopes, it's moving leftward. Good, you guys. Okay, let's draw some tangents on this one. This time the tangents will be underneath the curve. So now these tangents are starting off steep and sort of leveling off as you draw them. Till you get near the bottom where it's almost flat. So starting off steep, becoming less steep means that this is fast to slow velocity. And is this one going left or right? Good, left, because of the slopes of the tangents. Two more graphs and that's it. We're done for today. So two more graphs. Paste. No. I broke it, eh? Ah! Undo, undo, undo. Ah! Paste. Undo my undo. Okay, now we can draw some more curves. This one will start off slow and go fast. So start off slow and then shoot up. Oh, man, it's hard to do on this pen. Start off slow and then shoot up. Shoot up and then go slow. Hopefully by watching that might have made sense. Draw in your tangents. You can see the tangents are becoming steeper on that one. Here the tangents are steep and then becoming less steep. And that's actually how, a calculus course is started off, talking about tangent lines. So it's pretty cool. Physics and calculus are intertwined. I think is like the 16 or 1700s. I'm not exactly sure. I think it was 1700s. There's a black plague in England, and Isaac Newton, he left the city, went to a rural area to be alone in seclusion by himself, single-handedly wrote his physics, and then because he couldn't explain his physics mathematically, he invented calculus. Alone by himself in a rural area, invented calculus to explain physics. One of the most important human beings ever to live. Okay. So this one is also slow to fast, except we're moving right because of the positive slopes. And this one's also going fast to slow, but we're moving right because of the positive slopes. Okay? So that's it for the notes today. That was like a straight hour of notes. But I find that in physics, if you don't take care of the details in the beginning, when you go to do stuff later, it just won't make sense because you don't remember and you don't understand.
I agree with them totally. Wait, did I teach you physics?
Dirk.
Dirk taught you physics.
Yeah. Okay, so this correlates to 2.1 in your workbook. And I would ask you to get started on 2.1. There's two problems that the workbook does for you. You can look at them, okay? But if you could just get started, it's mostly a Science 10 review. And if you could get the first couple pages done by tomorrow, we'll take more of this up tomorrow, okay? So it starts on page 23.
Can you make sure that they show all of their parts?
Show their work? Yes, absolutely. Show your work.